in the last step, you basically come in and you add some anti-D3 branes down some long throat. This long throat is redshifting the anti-D3 branes, and their effect, which normally is very large, can be actually fine-tuned to be very, very small, and you uplift the anti-de Sitter to de Sitter. And again, this three-step scenario has been proposed by KKLT, and I think there are 3,000 other papers which have cited this work, which are working on this thing, and this is called the landscape. This is how you get a huge landscape of vacuum and string theory, which are all de Sitter and have stabilized moduli. Now, what's really happening, if you look more carefully in these constructions, is that there are three stages in these constructions. There's for the first stage, which is basically fixing up the complex structure moduli, which are the twisting shapes of this Calabi-Yau. Then you have the Kähler moduli, which are the overall volume and some other breeding modes. And the complex structure moduli are fixed by putting some fluxes on the 3 cycles. Again, this is some example. Again, all these things in the picture are 3 cycles, and I'm putting flux on all of them. The Kähler moduli are fixed by either D3 instantons or by Gaussian condensation confinement on the 7 branes, and that's a non-perturbative effect. But this is what you need to fix the Kähler moduli. And then the last step is to actually add the anti-branes, again, to uplift the cosmological constant. Now, these 3 steps are all done at the level of low energy effective theory, and the problem is, if you look at them in the full string theory, there are non-trivial ingredients which people didn't realize they are there, and these ingredients can cause problems when you try to mash up all these 3 ingredients together. When you look at the interactions between the string theory interactions between these ingredients, what you find is that, for example, the fluxes used as step 1 can have some problems with step 3. The fluxes, the anti-branes used as step 3 can destabilize some of the moduli which are stabilized in step 1. If you look at the fluxes by themselves, they cause a tadpole, and they can actually have cause you a self-consistency problem. If you look at the full string theory, and also there's a problem with confinement. When you put anti-branes, you can actually mess up the moduli stabilization, or maybe not. Maybe not. All these examples are some things where and what's happening is that if you work in a full string theory, you notice that you have to be much more careful. You have to be more careful with these ingredients, how you combine them. You cannot just dump ingredients, say, yes, I have all the Calabi-Yaus on the word, all the anti-branes on the word, I just put them there and everything will be hunky-dory and I'll get 10 to the 500 vacua. You have to be much more careful, and you have to basically build up, you have to be careful how you integrate the steps if you want to hope to obtain a nice beautiful de Sitter compactification. Now, and I call this Capezilla because it's basically saying that this naive way of just putting ingredients together is not working. And again, this is Scapezilla. This is a picture of Scapezilla, and this is the idea of the multiverse, of the idea that you have all these huge gazillions of vacua, and all of them are possible, and all of them are fine, and our universe is just somewhere there. And again,
Yusuf, you should go on. I'm not going to interrupt you too much, but let me say here, not working is far too strong a statement. We gave very explicit reasons for why effective field theory should be good, yes. And those scenarios can very well be possible.
No, absolutely.
Okay? So your statements are very strong. I want you to get to the end of this talk, so I'm not going to interrupt you anymore, but I want you to please be careful.
Yes.
Please exercise at least the same level of care we exercised in our papers, okay? Yes. That's what I want to say, okay?
No, so
please
I'm actually being careful.
I'm not going to interrupt anymore, but please go on, but be careful, please. Thank you.
Yes, no, absolutely. So what I'm saying, I'm actually being careful. So what I'm saying is that the scenarios might as well work, but the way people believe they work by just dumping together ingredients and ignoring their interaction is not correct.
I never just dumped the ingredients. I made sure we had parameters which would justify the use of effective field theory. 2 years ago, when some of you couldn't understand this, we wrote another paper spelling out why effective field theory would have to be good. So please be careful in your statement.
I will show you.
I'm not going to interrupt you anymore till the end of the talk. But please be careful. Don't exaggerate.
No, absolutely.
Thank you.
So I'll show you exactly why I believe in some things work and some things have to be fine-tuned, and some other ingredients have to be used. But I'll just this is the purpose of the talk, to show you that some ingredients have to be replaced. I think the overall picture may work at the end of the day. I mean, you'll see, it's an optimistic talk. But some of the ways of combining ingredients, I think they have problems. But okay, anyway, let me keep on going. So the first result has to do with the uplift. So when you put an anti-D3 brains and you have this long throat, if you imagine that again you have this calabiao, you put a long throat, the throat has a long jaw, and in this jaw there's a huge redshift. The prototypical example for this geometry is the Klebanov-Strasser geometry, and which has a 3-sphere, which basically stays finite at the bottom, and has a 2-sphere which is collapsing. And the solution has D3 charges dissolved in fluxes, which are imaginary self-dual. It's all supersymmetric. And when you come with anti-B branes, you can put anti-D branes at the bottom. And in the probe approximation, these anti-D branes appear to be metastable. However, the question is, great. I mean, and you know, they appear to annihilate against the flux in the cycles. So again, you have some non-trivial, again, to show you this picture, you have a huge D3 charge dissolved in fluxes, which is positive. You come with some negatively charged anti-D branes. They appear to give you metastable vacuum. And then these anti-D branes can decay and they can annihilate against these fluxes to come back to the supersymmetric vacuum. So you basically have metastable vacuum and the supersymmetric vacuum in the same theory. This is done in the probe approximation. And the question is, what's happening if you take back reaction into account? And we had some arguments that when I take back reaction into account, there may be some problems. And the reason is that in Klebanov-Strasser, in all these long warping throats, there are some fields which go logarithmically with the radius. They are due to the coupling constants of the running to the running of the coupling constants. So if you look in if you look in 4-dimensional gauge theories, all 4D gauge theories have a coupling constant which goes logarithmically with the energy. So whatever ADS-CFT dual, whatever holographic dual you are building for a gauge theory, which is a 4D n=1 gauge theory, you'll always have a logarithmic field in it. There's a logarithmic field, and in Klebanov-Strasser, this is basically the logarithmic field encodes the running of the difference of the inverse coupling constants. Now, anti-D3 branes couple to this field, and the intuition which you had in a paper with Nati Seiberg many years ago was that because anti-D branes couples to this field, they basically mess up the log at infinity, and when they mess up the log at infinity, you'll not get a metastable configuration, meaning that the energy of the anti-D brane will not be only stuck in the infrared, it will actually be visible all the way out to the UV. This is option number one, that the anti-D branes are going to couple to this field. There's another possibility that the log will not be affected by the anti-D branes, but then you basically get a singularity, which basically implies, I'll show you that it actually implies that you may have a tachyon. So this is the intuition. Now there's a calculation which we did, just took the anti-D branes, we did their full supergravity back reaction. And what we found was that when you put anti-D branes in this Klebanov-Strasser background, the anti-D branes can actually polarize, the flux is forced them to polarize, and there are two channels for polarization. One of them corresponds to a D5 brane wrapping a 2-sphere. The other one is an NS5 brane wrapping a 2-sphere inside the S3. And if you calculate this potential, so you can actually calculate the potential for the polarization along this blue channel or along the red channel. This is actually done using Polchinski-Strasser technology. It's a complicated piece of technology, but it's well known. It's a good piece of holographic technology. If you calculate the potential for the anti-D3 branes to polarize into NS5s, what you find is that there's if you just ignore back reaction, you find the fourth order term and the cubic term. This is the naive potential. But if you look at the back reaction, you find that there should also be a quadratic term. And then what's happening if you calculate this quadratic term? It was a complicated calculation, had 10 parameters in the game. You find that this guy is exactly 0. Again, very unexpected result. We didn't expect it. We're hoping that this result should be some positive number, but it came to be exactly 0. And moreover, you could argue that in other directions it's actually negative. And what this implies is that if you look at the anti-D branes, if you put a bunch of them on top of the North Pole of Klebanov-Strasser, they want to run away from each other. This is actually what we call a brain-brain repelling tachyon. The anti-D3 branes really want to run away. It's a very strange phenomenon. And actually, I remember when KKLT appeared, Shamit, I was a postdoc at UCLA, and Shamit asked me a message because I was the one who I knew Polchinski-Strasser very well, and he asked me a message. He sent me a message whether I have ever seen any example of this term messing up the polarization, and I told him no, because I had never seen this term, and it took us lots of calculations, and again huge amount of calculations in this potential to show that this term is really vanishing and some other directions are negative. It's a very weird behavior, but this is what's happening if you put anti-D branes again in Klebanov-Strasser.
Sorry, now, just to understand the slide,
yes,
you could go back to the
yes.
Slide. What is theta is how much it's blown up?
Yeah, theta is the angle on the three sphere. So if you think about the three sphere, if you just parameterize the three sphere with some angle from the North Pole, which is theta, you basically find the potential for this polarization. So this red guy, if you're in empty space and you put this red NS5, it will just collapse. The potential is theta to the fourth. Now, when you have fluxes, because you have fluxes in Klebanov-Strassler, which are some three-form field strength and some Ramon and SNS three-form field strength, they will talk to the NS5 brane. The NS5 brane will be pulled out by these fluxes, and this will give you a potential which is going to go like theta cube. That's the result. And then, if you look at the back reaction of these fields, of the anti-D3 branes, you actually find that there should be another term, which is over the theta squared, which is detailed balanced in this potential. So this potential has three terms, this, and this. But the point is, you can never ignore any of them, because whenever term 1 and 3 are equal, term 2 will also be important. Whenever term 1 and 2 are equal, term 3 will be important. So this potential has three pieces which are all detailed balanced.
Okay.
This polarization potential.
So the first term was the tension, was the
Yes.
desire for the thing to shrink down because that minimizes its tension.
Absolutely.
The second term was some flux blowing it up, and the third term was some nonlinear effect, you said.
No, the last term comes because if you look at the back reaction of the flux, so the point is, if you look at that background of the anti-D3 branes, next to the anti-D3 branes, you basically have ADS5 cross S5. You have some fluxes in ADS5 cross S5, some G3 and some F3, which back react. And there's a calculation by Friedman and John Minahan, pain, which actually calculated in the supersymmetric Polchinski-Strassler how these fields back react. And they back react on the dilaton, on the Ramon field with 4 legs along the D brane, and also on the metric. And what you can find is that if you look at this, if you put all this term together, they give you a term like this in the potential. And in the supersymmetric example, which was worked out again, if you just do supersymmetric ADS5 plus S5 with nice fluxes like in Polchinski-Strassler, this parameter becomes a perfect square. But in Klebanov-Strassler, which is non-supersymmetric, the fluxes are more ugly, the background is more ugly, the curvature is also important, and this term ends up being exactly 0. I'll show you on the next slide why this is happening from a gauge theory perspective also.
And the fact that it's a back reaction term shows up in the fact that it's proportional to ND3 bar?
Yes. It's the ND3 bar, and it's also the flux squared. I mean, I didn't show that, this term, the A3 term goes like the flux. This guy goes like the flux squared.
Okay, and one last question. So if you were working in the probe approximation, you'd see only the first two terms, and
yes.
within the probe approximation, you conclude it was unstable because of that.
In the probe
you're saying that the back reaction does not stabilize that probe instantly.
Yes. No. In the probe approximation, this potential looks to be stable. The problem was that because this guy is negative, okay, A3 is exactly 0, but you can argue that there's some non-diagonal directions. It's a bit more subtle, that in some other directions, this A3 will be negative. Now, if you look at A2, what it means, if you ignore brain polarization, so just kill the NS5, and just look at some D3 bars next to each other, the last term is the Coulomb branch potential. This is just the potential which the D branes feel when you take them away from each other. And what's happening is that this potential is negative. So if you just put the D3 branes on top of each other, they'll just run away from each other. So this is really the last term is really a Coulomb branch potential. It's really a Coulomb branch. Is really a Coulomb branch for this term. This is really the Coulomb branch potential for the anti-D3 interaction.
So what I'm not understanding is that last line. What do you mean other directions negative, sir?
Because okay, so what's happening is it's a complicated setup. So if you look at this thing, there are basically 6 directions on the NS5 on the D3 brane Coulomb branch. There are 3 directions up the throat, and there are 3 directions along the S3.
Yes.
And this potential is a more complicated function. It has actually, if you write it in complex coordinates, it has some Z1, Z2, some terms of the form absolute value of Z squared, and there are some other terms which are actually called Z times W. And the other terms are actually going to be there generically. Now, normally what's happening is that this term is stabilizing. So when you have this term big, even if the other terms are there, this guy is bigger than them, and so generically this term just dominates, and the other terms are not there. But when you have a generic setup, because this guy is 0, if the other terms have any value which is non-zero, that the branes will just run away in those directions. Those directions are some strange combination of the sphere and the conifold directions.
Okay, right. Thank you.
And I'll show you. So this is the picture from the anti-D3 brane perspective. Now you can also look from the point of view of so again, this is showing that there's a strange tachyon.
Iosif, let me say one small thing here.
Yes.
You did a beautiful analysis of all perturbations in the throat and so on. But first of all, do we agree that with one anti-D3 brain, there is no issue?
Coming up. It's coming up. Thanks for the question.
With
It's coming
more
up.
than one D3 brain, there is such a big warping factor that the anti-D3 brains will be pinned to the bottom, and they may distribute themselves along the bottom, but those are all compact directions, okay? Along compact directions, you can't have runaways, okay? So there could be more structure when you have more than one anti-D3 brain, but there's not a runaway in the problem. The system will find its minimum.
Yes. Yeah, indeed. So the only thing we found is that when you put them together, which is supposed to be the uplift, everybody's favorite uplift.
No, it doesn't have to. No, nobody said that. They just have to be at the bottom of the throat,
yes.
and then
I'll show you. There's another calculation. I'll show you in a second.
Okay.
Let me keep on going. This is some older
Okay.
stuff. I just want to go through it to understand a bit.
No,
So,
sure, please.
If you look at the anti-D3 brain, yes. Oh, there's another question. Sorry.
Yeah, could you go back a few slides? Another.
Okay.
And yeah, this slide here you have B2 integral over S2 that gives a log R, you're saying.
Yes.
There's some limit, there's some boundary conditions which gives a log R. You said that this is a field.
This is a
field, you said.
It's a field in the supergravity. In the holographic realization, it's a field. So integral of B2. This is the B2 of Klebanov-Strassler, the supersymmetric Klebanov-Strassler. Yes.
So how first of all, log of R, I mean, if R is dimension full, then you can't have log of R.
No, it's R over some conifold parameter. Sure. I mean.
Okay, and then log of R is some function, you're saying? R, it's some function of the field, you're saying, right?
Yes, the radius is like the energy. If you look at the holographic, if you look at the holographic theory, the radius behaves like the energy. So this behavior, B goes like log of R. If you translate to field theory, it tells you that 1 over G1 squared minus 1 over G2 squared goes like the log of the energy divided by some cutoff. And that's exactly the running of the coupling constant in four-dimensional gauge theories.
That gives you a function. I don't understand how it becomes a field. How does
No. So in supergravity, this is a field. In supergravity, integral of B2 is a field.
Oh, so log of R is just some function, yes.
Log of R is a function of the radius in supergravity, and then if you go to the gauge theory, to the dual gauge theory, it's the log of the energy.
Okay.
Because in the holographic dictionary, the radius and the energy are related.
Okay.
And this is exactly how you get. So again, for the gauge theories, all of them have the couplings run with the logarithmically with the energy. I mean, if you just increase the cutoff, you get a different.
No, I was confused because I thought you said log of R itself is like a field. That's what.
No. Sorry. No, that's.
Yeah. Okay. Good.
Okay. Let me get. So the picture is, there's a nice picture also, I mean, of this anti-D3 brain. If you look from their perspective, of their word volume, this is again valid in the regime of parameters when G string times the number of anti-D3 brains is much smaller than 1. Essentially, on the anti-D3 brains, you have n equals 4 Young mills. Now, when you put the n equals 4 Young mills into some 2,1 fluxes, they actually, again, the 2,1 fluxes of Klebanov-Strassler, they become 1,2 from the perspective of the anti-D3 brains, and they give you mass to the supersymmetric quarks. Moreover, there's a 0,3 field, which gives mass to the gauginos. So this supersymmetric Young-Mills theory will be deformed, first of all, by the red terms. Those are all supersymmetric terms, and they come again from the 1,2 fluxes of Klebanov-Strassler. And basically, these supersymmetric terms are going to give you some supersymmetric fermion mass and some boson mass. And then what's happening is that because you're in Klebanov-Strassler, at 3 level, you can actually calculate the full bosonic mass matrix. And what you find is that there's another term, which is the blue term, which breaks the supersymmetry from n equals 4, from n equals 1 star, which is the red Lagrangian, to n equals 0 star. And in this n equals 0 star Lagrangian, you basically have a flat 3-level potential. So again, it's a very weird n equals 0 star theory. It's a supersymmetry breaking theory, which at 3 level has a flat potential, which corresponds to the motion on the S3. I mean, again, if you just ignore the back reaction, this is just the free motion of the anti-D3 brains on the S3. Now, what's happening with this potential? This potential, I mean, there's a nice paper by Joe Polchinski and Andrea Pum and other people who are basically arguing that there'll be a correction to this potential, and there'll be a term which is going to be nice and positive, and therefore everything will be nice and tachyon free. However, if you compute this potential, if you look at the n=4 theory, again, n=4 super perturbed with these terms, you can show, it was shown by Parker and West back in '84, that this potential is flat to all orders in perturbation theory. So if you compute this potential, if you have this theory, which is it's a supersymmetry breaking theory, they have some very nice methods, which are, I mean, you can also calculate one loop and two loops using Jack and Jones and all the calculations in field theory, or you can look at this this argument by Parker and West. You can show that this potential remains flat to all orders in perturbation theory. So this flat direction, which we found along the sphere, this zero term, which the theta squared times zero term, which we found at in the supergravity using Polchinski-Strassler and using branes and back reaction, it's also then in field theory, and you can find that essentially you have a tree level, and to all loops in perturbation theory the potential is flat, and it's also flat when G string times n is much bigger than 1. So this makes us believe that this tachyon, this brane repelling tachyon, is still going to be there, even if we look in the regime of parameters when the branes don't back react. So this is again some way of matching things. So the conclusion is that if you put anti-D branes, let me finish. If you put anti-D branes and long throats, they seem to be unhappy. Now, sorry, questions.
So is this repulsion in the sphere direction, or is it like sending it up the throat?
It's some diagonal direction. So the only thing which you can see, we work next to the anti-D brane. So we are at the North Pole. There's the Earth, and there's the space. And when you go to the North Pole, the only thing which I can calculate, with precision, meaning like I can do a calculation with equal signs and not wiggles, is the potential next to the North Pole. So what I see next to the North Pole is that you have the anti-D branes, you put them on top of each other, and they want to run away in some direction.
No.
Now, of course, as Sandeep is saying, if you look at the full solution, maybe they go and maybe they stay somewhere else. Maybe they go and they just fly apart and they stabilize at some location. Absolutely, this could be the case. No, but the calculation we did just says that you put them on top of each other, and then they have problems.
No, let me say this, Shiraz. Let me explain the setup. Okay, there is a throat which terminates in a smooth geometry, which has an S3 at the bottom. This is the Klebanov-Strassler geometry. Okay, now a brane is BPS, so a brane has the Ramond 5 form pushing it in one direction and the warping pushing it in another, and it has no net force. The anti-brane, in comparison, has the 5 form pushing it in the same direction as the warping. So there's a huge force on the anti-D3 which pins it to the bottom of the throat. Okay, so therefore the only directions it can move in energetically are along the compact S3 directions. Okay,
that's in the probe approximation.
Okay,
in the probe approximation,
first of all, for a single, just single anti-D3 brane is going to be pinned to the bottom. Two of them will have some net force. There's a driving force at pinning them to the bottom. It will separate them a little bit while sitting at the bottom. Okay, these are all compact directions. I'm emphasizing again. Okay.
No, absolutely.
So Shiraz, I just want you to.
I get it.
Okay, thanks.
It gives you a structure, but it's not dangerous.
Yeah. Go ahead, please.
Okay. So
I have a question.
Yes.
So when you're talking about this flat directions for this particular potential,
yes,
you have fermionic terms as well as bosonic terms, right?
Yes. In the superannular theory, yes.
Yeah. So how does the cancellation happen between fermionic terms and bosonic terms?
Oh, it's a very complicated thing. I mean, if you can take this gauge theory, just n = 4 Yang-Mills, put this fermionic mass and put the bosonic mass, and you can compute. One loop, you can compute two loops, you can take Jack and Jones, you can put all the most general n = 1 theory, and you can compute the running of the coupling constant, and you can compute the running of this potential. And what you find is a huge amount of cancellations. And again, highly non-intuitive. I mean, everybody believes that this potential will be uplifted when you look at back reaction. Again, this is just Joe Polchinski who had that in his paper. So the people who are very serious. But everybody believed that this potential will receive corrections, and it will end up being nice and beautiful and curved up. But if you look at this calculation, and if you just input these things in the field theory, and you can compute one loop, two loops, and then even all loops, you can show that this potential actually remains flat.
No, it's okay. Just say we have the tree-level term. Okay, suppose we don't consider the quantum terms. How can the fermionic terms cancel? I mean, in order for this to be flat, for instance, suppose the tree-level term itself gives rise to the flat solution. Okay.
Yes.
So how can the fermion? So the fermionic terms have to cancel with the bosonic terms in some way.
Yes.
If the potential is to be flat, if the potential is to be zero, the fermionic terms have to cancel with the bosonic terms. That's what I'm not getting. How can that happen?
No. So the point is, at tree level, the only thing we look at is the bosonic potential. So there's a bosonic potential, which is again these two terms. At tree level, it's flat. It just it just happens. This is the setup. You have some branes in Klebanov-Strassler with some potential. At the tree level, this potential is flat.
Show me at loop level in supersymmetric theories, fermionic loops cancel bosonic loops. At tree level, there's no sense of that statement. Doesn't make sense.
No.
But then at one loop, the loops cancel. This is the amazing part.
Loops. I mean, there's this term which is a fermionic. I mean, if you say that only the bosonic term is considered, you will consider in this term.
He's looking at a potential for bosons. At tree level, they cancel. Now at loop level, there's something to ask, but at tree level, there's no sense of cancellation with fermions. Maybe we can, yeah.
If the full potential consists of both the fermionic terms and the bosonic terms,
he's looking at the potential for the bosons.
Then it's
position
okay.
of the brain.
Then that's
a bosonic field.
Then that's different. I mean, I thought it was.
Sorry, it wasn't clear. So anyway, the point is, anti-D3 branes in this throat, there's this problem, and again, you may not. I mean, you may believe that the problem is not there, but I think there's some problem. At least the standard lore, which has been around, is that anti-D branes are all going to be hunky-dory. They have this tachyon. The question is, maybe there's something else to use to uplift. And there's something which we are writing up with my student Pierre Heimann. There's a very nice class of solutions, which was found by Ba and Heimann, which involve non-trivial cycles of the transverse space collapsing. So it's some bubbling solutions which have a bubble here, which has some positive charge, and some bubble here which has some negative charge, and as well as a KK bubble. And the space-time is more complicated because you have the internal directions also collapsing. And this theory, for example, I mean, if you just look at this solution, it's a neutral solution. It has more mass than charge, so it's a perfect ingredient for uplift. Moreover, it's much easier to tune lambda, because normally when you have an anti-D brane, you come with the mass. The only way to bring the energy uplift to be small enough to avoid destabilizing all the complex structure and the Kähler moduli stabilization is to put it down this long throat. Klebanov-Strassler, log, interactions. And the point is, this solution, it actually can be, you can actually tune lambda much easier by just playing with these bubbles and these fluxes. And you don't need Klebanov-Strassler throats. You can actually do the uplift. Instead of putting some anti-D branes down some long throat and so on and so forth, you just put this piece of plumbing in the geometry, which involves, again, a vacuum bubble and some bubble with positive flux, bubble with negative flux. Moreover, this bubble cannot be put anywhere. Anti-D branes, you're at the bottom of Klebanov-Strassler, they move around. This configuration can only be put when the size of the Calabi-Yau directions has some particular size. And I think this is a feature, not a bug, but again, it's something to investigate. And there's another question whether this guy is stable. But I think the punchline which I like to make is that, again, anti-D branes, they're nice, but combining them with these long throats may have some problems. And this is an ingredient which I think is much more handy, because it gives you a much easier way to fine-tune lambda. And you get some nice smooth solution, and then nobody can say, there's an interaction, you have a singularity, you have some fluxes. This is all smooth, all bubbles and nothing. I mean, just bubbles and fluxes, nothing else. No singularities, no branes, no nothing. So the point I want to make is that I think there are some better ingredients to uplift, which again use this solution and some other friendly solutions which we are building right now. And again, they use this formalism which was found by Ibu Ba and Pierre Heimann on how to build multiple bubbles with positive and negative charge. So I think this is the point I wanted to take from the first part of the talk, is that maybe there are some better ingredients than the anti-branes. Of course, people can defend the anti-branes, but I think there are some better ingredients. Let me go to the second result. Again, this Klebanov-Strassler throat, which I discuss here, comes from warping the conifold. You have a conifold, and the conifold is deformed. There's a large S3. However, in flat directions, if you look at the conifold geometry, you find that there's a deformation parameter which basically shrinks the S3 to 0 size, and this is called the Klebanov-Zeitlin solution. So this is the deformed conifold. This is the undeformed conifold. Now, when you have the size of the 3 sphere, this is basically the conifold deformation modulus. When you glue this configuration to a flux compactification, then this modulus is fixed. But when you have an infinite Klebanov-Strasser solution, this modulus is actually flat. So one piece of intuition is that when you put this anti-de-brane on top of this configuration, you uplift the energy. You have a flat direction for the conifold modulus. Again, this S3 can be anything you want. You put this anti-de-brane, and then you actually collapse. And therefore, when you put an anti-de-brane, even a single one, basically the fact that you have a modulus in the original solution, again, when you add anti-de-branes to a gapped solution, no problem. The solution is gapped, you put anti-de-branes, But when you have a flat direction and you put the anti-de-brane is going to cause a runaway on the flat direction and collapse this configuration. This is my intuition. Again, before we started the calculation was actually very puzzling and revealed several things. First of all, if you calculate this thing, again, take a flux compactification, stabilize this throat. If you look at the potential for this modulus without the quantum correction term, you basically find this orange line. When you add quantum correction, this was shown by Douglas and Toroba, that the potential actually becomes bumpy and actually has a 0 at the origin. So the potential corresponding to stabilizing this jaw length modulus actually has a minimum, which is a supersymmetric minimum, but also has a bump. And when you add anti-de-brane, if you put a single anti-de-brane, again, I'm not putting 15 of them. 15 of them, again, I believe they want to run away and so on. If you put a single one, you come in with an extra piece in the potential, which is equal to this combination of the conifold modulus and the parameters of Klebanov-Strasser and so on and so forth. And what we found was that when the number of fluxes on the Klebanov-Strasser throat is smaller than 6.8, then there's a runaway. So, for example, when you have this number which is equal to 5, you put the anti-de-brane wants to cause the throat to run away. When you put the number is equal to 7, there's a very, very shallow minimum. When the number is equal to 12, then you have a metastable minimum. And this intuition was actually so this is again the calculation. Moreover, we basically so the intuition I had before that you have a flat direction, you put the anti-de-brane, you destabilize, is actually not 100% borne by the calculation. The calculation doesn't say that. So the intuition that you have a flat direction, you put the anti-de-brane, it will run away. It's actually not happening. And this is what our calculation shown. But then we said, okay, good. Anti-de-branes, they have more mass than charge. So when you put them there, they don't appear to destabilize the Klebanov-Strasser throat for large M, but then neither should a small black hole horizon. And then we conjectured in our paper that there should exist a Klebanov-Strasser black hole, which is dual to some deconfined phase of the dual theory, but which has chiral symmetry breaking. This is our paper, and we posted the paper on the archive. And next day, Alex Bushel told me that he had done the numerics, and actually he found that this black hole exists. And moreover, it's very cool that if you look at the range of existence of the metastable anti-de-branes and the range of the existence of this metastable of this Klebanov-Strasser black hole, it's a similar range. If you just look at all parameters, the black hole and the anti-de-brane metastable solution exist when G string times M is bigger than this combination of the number of anti-de-branes with a factor gamma, and gamma is 6.8 for the anti-de-branes and 4.16 for the black hole. But it's again two calculations done in different regimes of parameter. The black hole is fully back reacted. This anti-de-brane is just put in as a probe, and you can see that this phenomenon that when you put many anti-de-branes, they just cause a runaway of the throat. They just close the throat to close and to give you a singular solution is actually there. And again we made a nice prediction for holography.
Wait, so I thought you concluded that when the number of units of flux was large, this runaway was not there.
Yes, indeed, absolutely. So this is so we calculated. So when the number of units is small, G string times M is 5, then there's a runaway. When G string times M is 12, then there's no runaway for a single anti-de-brane.
But presumably gravity was only valid when M was large.
No. I mean, you have the Klebanov-Strasser solution exists for. I mean, if you put M over the 5, that's still a large solution. I mean, it's still a large throat. And I'll show you that there may be a problem with this throat. But let me keep on. So the point is, when this number is large enough, then everything seems to be hunky-dory, at least from the perspective of this throat stabilization. However, there's a more careful calculation which was done by Severin Lust and Lisa Randall, which basically showed that in our calculation, which we did with Severin and Emilian Dudash and Mariana Grania, we assumed the size of the 3-sphere to be constant. So we did this calculation in the Klebanov-Strasser solution, and we looked at the variation of the throat length and of the S3 size, of the throat length, but we kept the size of the warped S3 to be constant. And what they found was that if you include the size of the warped S3 and you allow it to vary, the potential we found, which again looks to be metastable, or here it looks to be unstable, gets a correction, and it actually becomes stable all the time. So Lisa Randall and Severin was on our paper, and then he realized that this term is missing, and then basically he found with Lisa Randall that this correction is there. So actually a single anti-D brane can actually give you a metastable configuration. Again, if you look in this field space, for every value of resting times M. There's a question, or?
In the previous slide, you were talking about the runaway to a singular solution, and that meant S3 shrinking to 0
Yes.
sign. Right?
Yes,
and
the warp
S3. You are
S3.
saying now you include that direction, or you. So I don't understand. I thought this is what you did earlier.
No. So the point is, if you look in the Klebanov-Strasser solution and you stay on shell, the warp size of the S3 is always the same. That's basically, I mean, it's just the way, because what's happening is if the solution becomes longer, the S3 of the conifold becomes smaller, but the warp factor blows up and it compensates. So the size is always the same.
Okay.
That's a feature of the on-shell solution.
Okay.
And if you look this, but this runaway, this potential is actually for the unwarped size, and you can see that it's actually going down to 0.
Sorry. And what is the size of the S? Ignoring the D3 anti-D3 brane, what is the size of the S3 as a function of M?
It's G string times M squared, I think.
In string units?
I think it's in string units. I have to look. It's in string units. Yes.
Yeah. So it's actually what Shiraz was saying, that, at least if parametrically, if you want S3 to be big in size compared to alpha prime, you need a big M. Now, exactly the numbers we can argue, but that's parametrically true.
Yes. No, absolutely. But I'll show you a bit later that this is also causing opening another can of worms. But let me finish up this calculation for the anti-D3 brane. So again, Randall and Lust argued that no, on the contrary, there is no runaway. You always have a metastable configuration for whatever value of resting times M is there. However, there's also another problem, because what they found is that the minimum, when you put the anti-D brane, the size of the S3, the unwarped size of the S3 becomes smaller. And because of that, there's a nice effect which was found by Kartru, Pearson, and Verlinde, which is the polarization into NS5s. And because the S3 becomes smaller, this is enhancing the polarization into NS5s, and can actually cause another decay channel. So that's something which at this point I think Thomas Van Riet and Severin Lust are working on, trying to figure out whether this is really going to give you something metastable, or because of the size of the S3 becoming smaller, you enhance this Kartru, Pearson, Verlinde polarization channel, and you'd actually decay in some other way. That's basically the status of this investigation at this point.
But suppose you polarize into an NS5, it'll become some NS5 on some equator of this, some circle on the S3, right?
Absolutely, at some value. But then the point is, if the S3 is very small, the NS5 will want to slide over the equator and come on the other side and annihilate. This is actually shown in the probe approximation by Kartru, Pearson, and Verlinde. Again, there's a small polarization, there's an NS5 again at some location. But then if the S3 becomes very small, the NS5 will actually want to basically slide over the S3 and collapse. So if you look in KPV, what they found is that the state is metastable only for P over M, which is the number of anti-D brane divided by the flux over the 8%. If it's more than 8%, it actually slides over. So that's But it's a different bound than the one we found here. The bound we found here also has G string in it. It's not just P over M. It's actually it's a different bound. It's a different decay channel.
Right. But at large M, we should never worry.
As large as M is large, I think everything should be hunky-dory. And we know this from the black hole. I mean, the thing which shocked me most, again, my intuition was you put garbage there, flat direction, it will run away, it will die. That was my intuition. But then we basically made this calculation for the anti-D brane, and now we found that even for an infinite Klebanov structure with a flat direction, you put garbage there and it doesn't die. And we made the conjecture for the black hole to exist. Again, nobody believed the black hole exists. I mean, Bushel, I talked to him for years, and he said, no, the Klebanov cluster black hole doesn't exist. You put a horizon, the S3 collapses. You put a horizon, the S3 collapses. You put any garbage, the S3 collapses. And then we did this calculation, and then we said, okay, it looks like you put garbage, you put the anti-D brane, and the S3 doesn't collapse. And it's happening in some range. And then again, Bushel came and, he actually found the black hole, doing full numerics, again, shooting functions of one variable, Klebanov structure, horrible stuff. And he actually found that the black hole exists. So again, it's really like a prediction from our calculation, which was confirmed by his numerics, by his numerical calculation. And moreover, if you look at the range, it's exactly the same parametric dependence on G string, on M, on square root of ND3. It's just that you get a different coefficient. He gets 4.16, but he does full back reaction. And you get 6.8, which is just the result of our proper calculation. But it's really the same. It's really the same parametric dependence. So the phenomenon is there, and again, when M is very, very large, things seem to be happy. That's the conclusion. When M is small, things are not happy. That's at least the black hole result. Again, Randall and Luce are saying that when M is small, things can also be happy. But again, I think this is going to enhance this instability, this Castro-Pearson-Velinde polarization instability, and there may be a problem with that. But anyway, that's a calculation which people are doing at this point. So until now, you can say, great, what's the problem? There's a runaway mode, but the mode goes away when G string times M is much, much bigger than the number of the fibrils. So why don't you consider a compactification which has a large G string times M, as Sandeep was saying, and get rid of it, no problem. Everything is going to be hunky-dory. The problem is that when you apply to the anti-D fibrils, this throat has to be very, very large. And the reason is that this is going to give you a hierarchy between the infrared scale in the UV scale, between lambda IR and lambda UV. And in the Klebanov structural potential, this hierarchy, again, needs to be very small. And this hierarchy, you can actually express it in terms of K times M, which is the flux, which is the DC flux of the throat, divided by this particular parameter. And this hierarchy between the bottom and the top, which you need, again, if you want to do a Klebanov structural uplift, is going to be expressible in terms of the Q in the flux, divided by, again, the 6.8 number squared with a factor of 2 pi over 3. Now, this hierarchy between the bottom and the top needs to be over the 10 to the minus 2 at least. This is basically the calculation. Again, if you want to get KKLT to work, if you want to put an uplift, if you want to put an anti-D brane, which uplifts your cosmological constant without messing up Kähler stabilization and complex structure modular stabilization, this hierarchy needs to be at least over the 10 to the minus 2. It can also be smaller. I mean, if it's smaller, it's even better because you uplift to smaller steps. But it needs to be at least this. If it's higher than this, it's going to cause a problem. Now, therefore, you can show that the hierarchy, in order to get a hierarchy between the bottom and the top, this throat, this Klebanov structural region, should have a flux, should have a Q3 flux charge dissolved in fluxes, which is of order 100. Again, that's the result of this calculation. That the flux, the Tadpole contribution from the throat will be of order 100. Now, okay. However, we have a compactification of string theory, and therefore, because you have a compact space, the Tadpole needs to be 0 totally. And the question is, how can we do this? How can we get a throat which has a charge of order 100 plus to cancel against something else on the Calabi-Yau to give me 0 in total? And again, to cite my good friend Master Yoda, lost 100 units of charge Master Calabi-Yau has. How embarrassing. It's embarrassing. We need to find another way to put 100 units of negative charge. Now you may say, great. How can you get 100 units of negative charge? Well, you can put orientifolds, but you cannot put too many of them because you get too many symmetries. You can put some D7 planes on some 4 cycles with a huge Euler number, and then you get a negative contribution, which is the order of the Euler characteristic of the 4 cycle. Or you can just work in M theory, and in F theory, the negative contribution is the Euler number of the Calabi-Yau 4 divided by 24. So you say, no problem. My throat must have charge minus 100, and this must be cancelled plus 100. You also have the fluxes of the Calabi-Yau, the rest of the fluxes in the Calabi-Yau, and this have to be cancelled by this contribution. Now, if you look in the Taylor-Wang calculation, the famous one which gives you 10 to the power 272 F-theory compactification, there's a Calabi-Yau there, which has a Euler characteristic of like 1,800,000 something. So the Tadpole contribution is 75,000. So you say, no problem. I have 100 units in the flux, but the Calabi-Yau has 75,000 negative units, and therefore there's no problem. I just cancel. I can just do calculation. I can just do flux compactification without any problem. But there's a problem. If you look at the Euler characteristic of the fourth cycle, it's actually given by this relation with the Hodge numbers, and in particular, those are the complex structure. Those are the Kähler moduli, and those are complex structure moduli. And when this number is very, very large, you basically have to show that you basically get a huge number. You get a huge number of complex structure moduli. Now, to stabilize this complex structure moduli, you need to put fluxes. You need to put, because again, all the complex structure moduli are stabilized by fluxes, as we discussed in the first stage. And when you put these fluxes, it actually give you a non-trivial contribution here. And the question is, how much contribution do those guys give you here in order to stabilize all these moduli? And the answer is that these fluxes will give you a contribution which is much, much higher than about 100,000. I'll explain you and I'll give you evidence in the future. And therefore, you cannot play this game. You cannot cancel 100 units of charges in the throat by just putting fluxes and by putting a huge negative Euler number, because this will come with a huge number of moduli. And when you want to stabilize this moduli, this is actually going to cause you, when you want to stabilize this moduli, this is actually going to give you a huge positive contribution to the Tadpole. And it will not work, because again, you get a huge number here, much, much bigger than here. And then we realize that, well, this problem is actually an open problem, has nothing to do with KKLT. It's actually long before KKLT. You can ask a question, just, in formal flux compactifications, how much Tadpole is sourced by the fluxes which stabilize n complex structure moduli? How many? Because again, you have many moduli, you want to stabilize them, you put some fluxes, but these fluxes, they source Tadpole. And the question is, how much Tadpole is sourced by them? This question is independent of KKLT and has actually been written. I mean, you can formulate it, just as a mathematically self-consistent statement before putting anti-brace, before any of this discussion. And what people have believed is that you just throw fluxes on the cycles. And again, the charge of the D3 is going to be given by the number of fluxes times some intersection matrix times some other thing. There are 10 to the 500 possibilities. And all these fluxes will stabilize the complex structure moduli. They can have any Tadpole you want. So for example, this is some flux intersection matrix. You put flux over the, one on the A cycle, you put 1, 0 on the B cycle, 1 on the A cycle, 0 on the B cycle. You put this other flux here, and you can get a Tadpole over the 1, or this, or even 0. You can just put huge amounts of fluxes without sourcing Tadpole. This has been believed, and this is at the basis of this calculation by Dan F. Douglas and Ashok of the 10 to the 500 possibilities. People just said, I'll just throw fluxes however I want, and everything will be fine. Everything will be fine. However, I'm a Romanian. Mind tricks don't work on me. If you just tell me that everything will be fine, it doesn't work. I need to see something more concrete. I need, something. I need to see something. I need to see this phenomenon realized in some honest to goodness solutions. Now, there's one example.
You should go on, but Iosif, people were not quite so naive. I mean, there was a thinking behind that, And of course, it's good to do explicit examples, but their basic thinking was that every period would typically depend on all complex structure moduli. And order 1 fluxes would give a source term for every period. So there wasn't a essential tension between the number of complex structure moduli you had to stabilize and the total orientifold charge.
Indeed.
That was the thinking.
Indeed.
But of course, we should investigate it more. But I'm just saying that is the context. And,
Yes, absolutely. No. So, those guys are very smart. I'm not saying, this problem has been, again, everybody in the community, 20 years, and everybody has believed this thing. This is, the intuition is very clear. You put some tiny amount of fluxes, they couple to everybody, and therefore, they'll just stabilize all the moduli. It's a very good intuition. And moreover, there are some examples of K3 times K3, for example, which have been stabilized with some singularities with this thing. So, but
allow me to say, worked out by my postdoc, Prashant Tripathi, first with me anyway. Yeah.
Okay. Good. So the point is, if you look at this intuition that, you just stabilize all the fluxes with supergravity solutions, we can ask what has been constructed. Can you actually build solutions like that? And we have a huge amount of geometries which have been built up by, fully back-reacted geometries which have been built up by Nick Warner and I, which involve bubbles of flux. And these fluxes are actually wrapping some bubbles and they're actually stabilizing them. And they're self-dual fluxes. And they look exactly like, if you look at what's happening, you have some fluxes which are stabilized by, some bubbles which are stabilized by fluxes. And these fluxes source M2 charges. And therefore, they correspond to microstate geometries or fuzzballs of the M2 black hole. That's something which, and you can also compactify them to 10 dimensions. They become some DNF type multi-center solutions. And the question is, can I actually get what's the tadpole, what's the M2 charge of the full solution for a given number of bubbles? Or otherwise, given some fixed M2 budget, how many bubbles can I blow up? Is the number of bubbles going to go like n to the 0, as people have? Again, this is what the DNF Douglas calculation would imply. Or is it going to go like n to the 1, or is it going to go like n squared? Now we did a calculation, fully back-reacted solutions, with all the metric and so on and so forth. And what we found was that the number of fluxes, the charge which is sourced by this, which is sourced by this, the charge which is sourced by these fluxes is of order n squared. So basically, you can only, when you have n bubbles with flux of order 1, you basically you get the charge of order n squared. So basically, the number you cannot stabilize a huge amount of fluxes with a given charge within a given tadpole. And moreover, and the reason is very simple. You have a warp factor in the problem. The warp factor is called Z, which is sourced by G. Now, G, the integral of G is going to be of order 1. But this is happening generically. This will be a non-trivial function which will have both negative and positive regions. And when you put random fluxes, if you just throw some fluxes on the system, G will have a negative region, and therefore it will give you a negative source for the warp factor Z, and the function Z will want to be negative. And once you put a warp factor which is negative, you have closed timeline curves and imaginary metrics and the whole shebang. And what we found in our example, again, those are worked out solutions in detail, is that the charge of the charge of the system has to be of order the number of stabilized moduli squared. You could not get smaller Q total. That was the calculation, again, using bubbling geometries. Now, and moreover, if Q would be of order n to the 0, so if the Dennis Douglas intuition were realized, and the number of brains would go like n to the 0, you could blow an arbitrary number of bubbles with a fixed total charge. So I take a charge which Q, which is 1,000,000, and I can blow an infinite number of bubbles. And therefore, because I can put all of those things in ADS, I can actually overcount the black hole entropy. I can build more solutions than the entropy which the black hole has. So this is clearly a problem from the brane perspective. However, I'm not saying that this could be of order log n, or like n to the 1/4 or n to the 1/2. It will still be happy for the black hole entropy, and it will still be happy for the flux compactifications if Q were not going like n to the 0, but n to some small power. However, we ask the question, how many fluxes do you have? And there are actually 3 incarnations. You can go in type to B, and you can say, okay, I have H2,1 complex structure moduli stabilized by 3-form fluxes. There's some F3 fluxes, some H3 fluxes. They form a basis. You have they form a basis. And the question is, how much is the Q sourced by these guys when all the fluxes are stabilized? And how does Q grow with H21? There's another question having to do with the 7 moduli. Again, the 7 moduli is stabilized by some word volume flux F2, which lives on some rigid curves. And the question is, again, if I have some D7 branes, how much Q is sourced by this F2, which stabilizes the D7 brane moduli? You can also ask, if you just take F theory on a Calabi-Yau 4, you have, again, both the complex structure moduli in type 2B and the D7 moduli. You put them together, they form 3,1 complex structure moduli on the Calabi-Yau 4. And the flux is combined into 4 fluxes in the Calabi-Yau 4. And then there's a tadpole in the fluxes, again, given by G4 where's G4. And this tadpole has to be smaller than the Euler characteristic of the Calabi-Yau divided by 24, because this is basically this is the tadpole cancellation. And this number grows with an H3,1 like this. So you can see that if the Q of the fluxes is bigger than 1, if the coefficient here is bigger than 1/4, then there's a problem. There's a problem with all flux compactifications, supersymmetric or not, ADS or flat space or anything. If you want to stabilize and stabilize all the complex structure moduli, again, this is step 1. This is before putting anti-branes, before putting KKLT, before stabilizing Kähler moduli. Long before that, there's a problem. If this number is bigger than 1/4, then there's a problem with this. Then there's a problem, and you'll never be able to stabilize all the complex structure moduli. And basically, so again, this is the number, and for large H3,1, basically this number is, again, as I said, a quarter of the number of moduli which is stabilized. Now, what are the answers? We did a whole bunch of calculations. We actually calculated, and people also did the calculations, for many systems with a large number of complex structure moduli, large-ish. And basically, you can ask how many, what's the charge needed, what's the charge of the fluxes which stabilize these guys. So if you take type to be on some highly symmetric spaces, Sandeep and Ashanta and Shamit have this calculation, and again, we just took the numbers, 0.48. If you take this other calculation by McAllister and friends, it's 0.46. If you take F theory on Sexti Calabiao, it's again this number. F theory on CP3 base, Corinucci, then Fesole, again, those are the numbers. This is the calculation. Then we had this postdoc who is a very good mathematician who actually knows very well, how to do horrible calculations, and he was actually to show that if you take F theory on any weak Fano base, and so that's a special class of F theory compactifications, and there's an uncountable number of weak Fano bases. So we're talking about an infinite number of manifolds here. The number of the 7-brane moduli is actually goes like the Euler characteristic cube of this, the integral of the cubic Euler characteristic of the Q1 cube of this background, which is 58 times this plus this number. The Q flux minimum goes like this, and the number is going to be over the 0.44. We also did the calculation for M theory on K3 times K3. Again, there's one difference between our calculation and all the previous calculations. We wanted the smooth solution. If you assume singularities, of course, you can compactify everything. And if you assume singularities, you can actually compactify moduli with much less. But then singularities have their own things. They have gauge theory living on them. There are degrees of freedom and so on and so forth. But the mathematically self-consistent question, which is, how many moduli can you stabilize? We did a huge number of calculations here using machine learning. And again, we found a similar number. Then
But sorry, I have to interrupt. Even before the calculation with Geryavets, Kachru, etc., Prashant and I wrote a paper where we did K3 cross K3, and
Yes.
all the singularities are simply D7 branes coming together to give non-abelian gauge theory.
Absolutely.
So they're
But
absolutely, completely in control and fully understood from every viewpoint. I just want to say that.
Indeed.
There's nothing mysterious. It's as simple as 7 branes or branes coming together to give. Okay. So, anyway, just wanted to say that.
No, absolutely. So the point is, this calculation, and there are also other calculations saying exactly the same thing, that if you allow singularities, this calculation of ours is just 3-level, classical. Sure. And if you look at the 3-level calculation, again, you get this potential. Now, when you put the 7 branes on top of each other, then they have an SUN theory living on them. And the number of degrees of freedom actually increases. If you just look at 3-level degrees of freedom, the number of degrees of freedom actually increases when you make singularities. So if you want to stabilize classical moduli without invoking quantum effects, without invoking confinement and so on and so forth, then I think bringing branes together is a losing game, making singularities, because these singularities have degrees of freedom living on them. The cheapest way, again, our calculation was actually, the question we asked was different. If you have a smooth solution, then how many fluxes do you need? Then of course, and this is a classical level question. Now you can say, okay, great, I accept the 7 branes, I put a lot of them, there's a confinement on them, these degrees of freedom get uplifted by confinement, absolutely. But that's a quantum effect. These calculations are all classical. This is all saying at the level of classical effects, the way you stabilize moduli the way you stabilize complex structure moduli, you basically build this, if you want a smooth manifold, that's how much flux you have to put. There's another calculation by Grimm and Mariana. Sorry?
The question is, what exactly do you mean by moduli stabilization? It's giving masses to the moduli?
Yes, classically.
Yeah, classically. Yeah. So
the way complex structure moduli is stabilized generically, again, you have some bubbles and you have some moduli and you put fluxes and this moduli are stabilized.
Right. Now, in the initial potential term that you had, which you said was kind of, you look for flat directions and things like that. That itself had terms which were mass terms. So So moduli already had masses. So I don't understand
In a
why.
Calabi-Yau compactification, there are most of the moduli don't have masses. So for example, just take a torus. When you compactify on a torus, the size of the torus can be anything. And then
so
you can also compactify.
Apart from those moduli, there were other moduli which are massless.
Yes.
Is what you're saying?
Yes. So generic.
When you do the quantum corrections, those will also gain masses. That's what you're saying, right?
No, so those moduli normally are stabilized at the classical level without doing anything by just putting some fluxes. So if you take a Calabi-Yau, which has many moduli, if you put fluxes on the cycles, if you put a lot of fluxes, you can show that there's a potential for this moduli, and this moduli gets stabilized generically.
But then you also have to do quantum corrections, right?
Indeed, but the point is, the step one of the stabilization of KKLT, and the step one in the stabilization is a classical calculation. The classical calculation is I have some flat directions, I put some classical fluxes, I compute the flat directions, and then I just find a stable solution. Now, quantum corrections are problematic because if you have a massless direction, quantum corrections can either stabilize you up or down. And if you look at the quantum corrections, they could give you some runaway terms. So for example, you can have a quantum, you can have a theory which has some singularity, and or some flat directions. If you compute quantum corrections, these flat directions are going to correspond to a runaway. So if you want to get vacuum with stabilized moduli, you have to find a place where all the moduli are massive, are positive, or all the masses are positive. And that's quite non-trivial, but classical fluxes do that. I mean, this is the nice part about flux compactifications. If you put classical fluxes at 3 level, they just stabilize all these complex structure moduli to some nice compactification.
I see. And are there any flat direction for the fermions? Flat fermionic?
No, fermions are happy. Okay. Because the fluxes uplift them, so fermions are happy. So this is the calculation again done by Mariana Grania and Thomas Grimm in this and her postdoc Alvaro Herrales in this asymptotic Hodge theory. So again, they're taking Calabi-Yaus in some funny limit, and again they found this number to be bigger than 0.5 times the number of moduli. And recently there was a paper by Katrin Becker and Valher and Vrase and Gonzalo, which is doing some Landau-Ginzburg model, the worst place where you expect the Tadpole conjecture to be correct. And there, they also found that, there's some moduli and, there's some flux. And this number came again to be bigger than 0.46. We're quite shocked by this result. But you can see there's some universality here. The ratio between the fluxes that are stabilized and the number of moduli, if you want no singularities, again, if you want to be at the classical smooth solution, then this number appeared to be bigger than, something over the 0.4, 0.3. And we made a conjecture basically saying that, this number grows linearly with n, and basically this number has to be bigger than 1/3. Now, I want to make a remark. Generically, this Q min is the minimum value.
Where did you come up with this conjecture? What is so special about 1/3?
It's basically just try to make
a few examples have been done and you come up with that's the basis, right? I just want to make sure it's not a mathematical theorem.
No. The theorem. So the theorem is here, for example. This is the theorem. If you do F theorem on any weak Fano base, those are the numbers. This is actually the number is 7/16. So that's basically 0.46 something. But that's a special example. The number in your example. Sorry?
That's some example. I'm just saying, is there a theorem which says the following?
No, it's a conjecture.
Oh, and by the way, we only need to stabilize the non-compact moduli, okay? Even complex structure moduli can be broken up in being compact and non-compact. All that's important really is the non-compact. What's the theorem which says for a Calabi-Yau compactification, this is the bound? There is no such theorem. In fact, that there's a paper recently by Severin, Lust, and collaborators, which itself shows that you can do much better than this bound.
Oh, no, Severin's paper is actually doing much worse. No, that's the whole point. Severin's paper is actually doing much worse.
Okay, but first of all, we can discuss that, but this is not any theorem, okay? I just want to make sure.
No, this is not a matter of theorem.
Data, that's all it is.
Absolutely, no. At this point, we only have examples. Again, we are being experimentalists. We just solved all these examples. Again, F theorem on any weak Fano base, M theorem K3 times K3, wanting a smooth solution with no singularities, people who do asymptotic Hodge theory. Again, all these things have been worked out. And these numbers come out like this. That's a fact. Now,
nobody has bothered to classify which are compact and which are non-compact. Okay?
Absolutely. But then Vafa, for example, he believes that, there's no distinction between them. And when you go to F theory, they mix. And what appears to be a compact modulus is just an artifact of working in type 2.
But it's a
and if you look in F theory, everything will be non-compact.
No, it's a perfectly well-defined question given
Absolutely.
a moduli space, how many non-compact directions there are.
Absolutely.
Okay, it's a completely well-defined question.
Absolutely.
That's the relevant question here, by the way.
I'm just waiting for everyone. I mean, so the point is, I mean, we thought about this quite a bit, and then Vafa basically beat us down. He said, no, all the modules are non-compact. All the complex structure modules are non-compact, because if you go to F theory, it's all non-compact.
Even on K3 cross K3, you can see clearly that complex structure moduli, some are compact and some are non-compact. Even in that simple case. We can go over that example.
Yes, no, but that would be good. I mean, that would be actually so that's that's a refinement of the conjecture. At this point, again, the conjecture. I mean, people who did all the DNF Douglas argument and so on and so forth, they all said
another question.
Yes.
Another question. Like, when you have these, do you have finite supersymmetry in your model? Do you have n equals 1 supersymmetry?
Yes, in these examples, there's n equals 1 supersymmetry.
Yeah, so there would be, for the super partners of the moduli which are flat, which are massless to start with, you would have some fermionic directions which are also massless, right? The super partners.
It's actually unclear, because these n equals 1 theories are actually confining, and when you confine, I think the super partners are going to get a mass.
So supersymmetry is broken then?
No, it's just confinement. N equals 1 theory with confinement, doesn't have flat directions.
No, if the fermions and the bosons do not have the same masses, and the supersymmetry gets broken, right?
No, but the confinements, so in a confining theory, they both get the same mass, but they're all massive. So I think classically, if the fermions get what I understand, but again, maybe Sandeep knows better. If the bosons are stabilized, the fermions are also stabilized, because it's a supersymmetric theory.
No, that I understand. But to start with,
there's no notion of flat directions and fermions, right?
No, I'm saying flat directions in fermions in the sense that to start with, they might be massless, because if you start with massless boson, then the super partners would indeed be massless to start with. Maybe with quantum corrections, they might receive masses, and fluxes, they might receive masses. But to start with, they have to be massless, right?
True.
That's what I'm saying.
Sure. But let's say while preserving supersymmetry, which you could do for lifting the complex structure moduli, if you lift some of the scalars, then you lift the fermions and give them the same.
That I agree. Yeah.
I think that's this is the logic. So that's why we're only focusing on bosons and not fermions. I think that's so. Indeed, so coming back to this, absolutely agree with Sandeep. If there's a distinction between compact and non-compact and so on, there's a refined version of this, which is actually the question: what's the number alpha for compact moduli? And there's another refined version, which is okay, great. I have singularities. All these numbers don't want singularities. All these numbers assume no singularities. However, if you allow singularities, which could correspond to D-branes, and then you allow quantum effects on these singularities, meaning you can have some D7 branes which have n squared degrees of freedom, but then they confine, and the number of degrees of freedom becomes 1, and therefore they basically so confinement can also kill some of these complex structure moduli when you have singularities. The only thing I'm saying is that, again, the DNF Douglas shock calculation is basically being a bit cavalier. There's a more subtle calculation. This assumption that you can just put any flux you want and everything will be hunky-dory is not correct. Again, all these numbers are basically going in the wrong, are basically showing that there's a problem. And basically, one needs to go back to the drawing board, and one needs to basically calculate these things. And one has to calculate. I mean, I would love to see a calculation which says for compact moduli, the number is like 0.27. If somebody does a calculation like that, I'll be like, no, I'll be ecstatic. It's just that I haven't seen any calculation in that direction. So, and all the calculations are in the literature. Again, those are done by us, and those are done by us, and the rest are done by other people. Again, they're not, and who are not exactly anti-landscape researchers, but those are the numbers which come out. If you assume a compactification, if you want to stabilize the fluxes, if you want a smooth solution, that's what you get. Those are the numbers. And our conjecture, we just conjecture. I mean, again, it's a conjecture. It's not something, you know, if people find a number below 1 point, below, so we thought it's something over the 1/3, but again, it's just based on intuition. For this fun of things, it's like, you know, 7/16. Here it's a different number. Here it's like, you know, 0.46. In this particular, it's, you know, 12/26. It's a different number. You know, here it's, you know, 25/57. It's a bit different from 0.44. So all the numbers come out in the same range, but it's not exactly the same number. So that's why I made a conjecture with some reasonable small number. But again, the conjecture we made is, you know, bigger than 1/3, because, you know, everything seems to be bigger than 1/3. But generically, again, the number of fluxes will be over the n squared. We spend a huge amount of energy finding these vacua. If you just put a random flux compactification with n moduli and you want to stabilize them, generically you get n squared tadpole. You'll not get tadpole over the n. This is just the minimal number you can find. Okay, let me keep on going. I have so again, the implication is that, you know, if you don't make the distinction between compact and non-compact, you know, if you believe Wafa that, you know, they're all in the same ballpark and you should stabilize all of them, otherwise there's no compactification, then there's a problem, because again, the fluxes, which the negative tadpole can be over the 1/4 of the number of moduli, and the tadpole you get is actually over the 1/3, and, you know, 1/3 is bigger than 1/4, so you'll never be able to find a huge amount of vacua. So, for example, all these F theory vacua with large H31, you know, all these 10 to the power 272,000, they'll all have flat directions. They all have flat directions. That's basically the result. There's something about the sevens, but, you know, we can discuss later. So coming back to the sitter, again, it seems to be that, you know, one anti-brane, it can be done. You need a charge of order 100. That's very hard to absorb, again, unless you want to make this distinction between compact and non-compact. It's hard to do with O3s and O7s and D7s according to the Tadpole problem. There should be some ways to go around. First of all, maybe you don't need the hierarchy. Maybe you don't need the long throat. Again, what my solutions with Pierre Heidemann are showing, that, you know, you may be able to uplift without getting this long throat, without needing any of this thing in the calculation. You don't need, again, this Klebanov-Strassler throat is not going to be there. You just put these bubbles somewhere in the Calabi-Yau here, and you uplift with them, and you don't need to worry about all this anti-D-brane Klebanov-Strassler business. You just throw it away. That's one possibility. Maybe it's like that, maybe it's not. But again, that's basically one possibility. Maybe you can do a smaller hierarchy. So, you know, Quevedo and Valandro are basically argue that, you know, for LVS you need a smaller hierarchy, and therefore maybe it can be done. However, there's some arguments by Susha and Yvonne Zabali and Yvonne Zabala and Chakraborty that, you know, and Bento, that, you know, you can get a sitter with no hierarchy. There are some sitters with no hierarchy, and one solution is that also, you know, maybe you can, if you assume, I mean, if you look at these calculations, you can also get some de sitter in some other scenarios. So, for example, one thing which we wrote this spring, there's something called the bare bones de sitter. When you put this 2,1 flux to fixed moduli in KKLT, you need to add also some 0,3 flux to give you some non-trivial W0. But what we found was that if you put the anti-D3 brane, it actually sources some 0,3 flux by itself. And you don't need to put this W0 by hand, which again, KKLT needs to put. The anti-D3 branes are going to give a non-zero W0 to begin with. And then this step of KKLT is not necessary. And you get a nice, beautiful de sitter, again, assuming one anti-D brane is hunky-dory and ignoring this Tadpole problem. And we call this bare bones de sitter. You know, you can get some other compact. I mean, if you're careful about the ingredients, I mean, the main point I want to make, if you're careful about the ingredients, you find that, you know, some steps are a bit cavalier, are done a bit too fast, but you can discover some new physics, which actually can make things much easier. So again, anti-D3 branes can actually help at this first step of KKLT, for example. That's another calculation. Now, there are caveats again in the tadpoles. They are done on supersymmetric spaces with special properties. Maybe less symmetric spaces are going to be different, but again, there are 10 to the 15 toric bases, which, you know, which seem to satisfy the Tadpole conjecture. The weak Fano class is bigger than toric class. Well, apparently is uncounted. I have no idea why. That's a mathematician. You can ask a mathematician-friendly guy if you want. But there's a huge amount of examples when, you know, it appears that the Tadpole conjecture is satisfied. There are some scenarios that, you know, maybe you can stabilize with moduli of order 1, but they have been worked out by Severin and also by Green, Plaushin, and Van Heisteg. And you show that, again, the number of of the charge always goes like 0.5 times the number bigger than 0.5 times the number of stabilized moduli. That seems to be the calculation again in this corner. So there's some claims that people can stabilize with the tadpole of order 1, but it doesn't work. And I want to finish by giving you some example and of why this doesn't happen, some intuition. I mean, I want some physical intuition. I mean, this is all Calabi-Howell-ology with like many fluxes and so on. I want to give you some physical intuition why this happens.
You should give that definitely, and please do conclude also.
Yes.
But afterwards, this is a bit technical. I wanted to ask you about the recent paper of Severin with this other guy, Weissner, because they don't stabilize all the moduli. But if you look at the ratio of what they stabilize and how much orientifold charge they consume, it's below your bound. Anyway, the bound is conjectural, but I want to ask you, but I think there's an issue with their paper because the normalization of fluxes isn't quite correct. So I'm told. So this issue is kind of important in general. I think if we are going to compute orientifold charges reliably. So I just want to raise it. I'm not an expert, but it's an issue that Liam is hammering at least me about. So we'll discuss it at the end.
Yes,
okay,
absolutely.
Please.
So the point which I want to make is that, again, the intuition that you just put some fluxes on a Calabi-Yau and everything will be fine. It comes from the very simple argument. You just take a Calabi-Yau, you take a basis of 4 forms, which are basically self-dual, and you basically write, not self-dual, you just write a basis of 4 forms. You just write some omega A, and you write your flux as some NA, which is quantized, times omega A. Now, if you look at the Tadpole contribution, again, the contribution of the G4 flux to the D3 to the D3 charge in F theory, it's equal to 1/2 times integral of G4 where G4, and this gives you some flux vector times some intersection matrix times another flux vector. And naively, again, I have an intersection matrix, and I just put some flux and I put another flux, and naively I can get this quantity to be anything I want. However, if I look at this flux, again, this is the flux written on this basis. When you go to the minimum, if you want to get a supersymmetric solution, at the minimum, G4 is equal to star G4. And therefore, if you look at the integral of G4 where G4 over the Calabi-Yau manifold, this will also be equal to, this is a local constraint. So this integral will be equal to G4 wedge star G4, which is going to be a positive number. So the integrand of this quantity will be positive everywhere. And if you have a huge amount of fluxes here, and some of them give you negative contribution, some of them give you positive contribution, there'll be trouble. And to see this, take one example, which is, basically people's favorite example taken by these guys also to give this thing. Take some manifold which has A cycles and B cycles. Those are the A cycles, those are the B cycles. And you put some flux 1 on the A cycles, you put flux 1, 1, 1, 1, 1 on all the A cycles. And you put some flux on a B cycle, just on one of them, which is over the FB. If you look at the intersection matrix of the Calabi-Yau in A cycles and B cycles, this is the intersection matrix. So if you just put these fluxes, again, you put everything on the A cycles and a tiny weeny amount on the B cycles, you found the tadpole, which is of order 2 times FB, which is very small. Again, I have n squared, I have n cycles, I put fluxes on all the A cycles and put 1 flux on the B cycle, my tadpole is of order 2 times FB. However, if you look at the G flux and you decompose it in terms of this basis, you can write G as G on this cycle, this cycle, this cycle, this cycle, this cycle. And if you look at the result of the integral, if you integrate, for example, G on the 3 cycle on this G, sorry, let me annotate. If you integrate, for example, this G against let's say this is G3 against this G, you'll actually get 0. There's a 0 in the intersection matrix. And this tells you that this integral, for example, of G3 where G2, the guy on the second basis and the guy on the third basis, is equal to 0. And there's going to be a huge amount of integrals which are going to be 0. The only thing on 0 will be actually the integral of G1 where G2, the G on the 1 cycle. So this guy talking to this guy, this will be non-zero. Everything else will be 0. And therefore, you have n order of n vanishing integrals on this Calabi-Yau. Again, if you integrate these quantities on the Calabi-Yau, they'll only give you 0. And one quantity will give you something positive. Now, if you look at the, sorry, let me clear the annotations and go move to the next slide. if you look at the and get rid of this, if you look at the Calabi-Yau, again, I told you that there's going to be a huge number of integrals, which is going to be 0, and a few of them which are going to be positive. When you have an integral of g2 where g5, for example, equal to 0, the integrand will be positive somewhere and negative somewhere else. So let's say I break the Calabi-Yau into 2 parts. It could be even more. In some part of the Calabi-Yau, the integral will be positive. The integrand will be positive. In some other part, it will be negative, and the red integral will be 0. If I look at the integral of g3 where g2, again, some other flux components, the integral is 0. At the level of topology, the fluxes have no intersection. But at the level of the integrand, this will be a positive quantity somewhere and a negative quantity somewhere. And generically on my Calabi-Yau, I'll actually have basically for every integral which vanishes at the level of the cohomology, I'll actually have a positive integrand somewhere and a negative integrand somewhere else. If I come up with some other integral, if I come up with g2 as g7, like another piece of this calculation, again, this will give me some regions of 3 positive contributions, 2 positive and a negative 1, 3 negative ones, and so on and so forth. And then I come in with the last integral, which is going to be positive, which is over the 1, which is giving me a tiny positive piece everywhere in the best scenario. Now, you can see that I have a problem because this quantity, g where g, integrated everywhere, the sum of all these guys has to be positive everywhere. And generically, I have some regions where there's a huge amount of negative contributions of order n negative contribution, which have to be cancelled by 1 positive contribution. And this calculation is not done at the level of the metric. This is just done at the level of topology. This is done before putting any metric on this Calabi-Yau. Then you can come and say, yeah, I have a metric. I'll put my Calabi-Yau, I'll squeeze it, I'll squash it, I'll do something else. But these regions remain. These integrands are done at the level of topology on the Calabi-Yau. They're not done at the level of the metric. And therefore, if you just put a huge amount of fluxes, which give you small tadpole or tadpole of order 1, you are guaranteed to have some regions of the Calabi-Yau which are going to have mostly negative contributions with a tiny positive 1, and you'll never get a clean solution out of that. You'll always have a singular solution out of that. And that's basically the intuition why this is not going to work, why you cannot stabilize a huge amount of fluxes with with a tadpole of order 1. Again, there are 2 to the n regions when you have n fluxes, and some of them have n negative contributions and 1 positive contribution, but the whole sum has to be positive everywhere. And this is very, very hard to get. And generically you get the negative War factors, and the metric will scream and so on. This is the intuition behind the tadpole conjecture. This is the intuition why things don't work out. So that's so again, at the risk of getting Sandeep a bit annoyed on me, this is the trail of destruction of Scape-Zilla, which is basically the work which has been going on. Before 2010, everybody said all anti-brains are okay, multiple anti-brains, everything hunky-dory. Then people said anti-D brains, Joe Pochinski and other people, and at distinct times much smaller than n is okay. Then again, we showed that it doesn't. A single anti-brain is okay. Sometimes it is, sometimes it isn't. Then there'll be a tadpole. Again, the only way it's okay is if there's a tadpole of order of 100, no problem. It will be cancelled by the 7 brains. We showed that it doesn't work. F3 saved the day. It doesn't work. And the point is now, again, there are some other things. Of course, one has to check. One has to do the calculation. There's, as Sandeep is saying, maybe you have singularities. Maybe you have confinement. Maybe you have non-perturbative effects. Maybe you have a distinction between stable and compact and non-compact moduli. Absolutely. And I think people should do the calculation. People should do the calculation on this. Sorry, somebody's calling me. I need to hang up. So people should do the calculation to find and. Sorry, let me get this. Let me get this. So I think there's a problem with uplifting in warp throats. I think the way to get the sitter will not be by anti-brain uplift. I think there will be another way to get the sitter. I believe there should be the sitter, but I think it will become with some other ingredients, but not up anti-brains in warp throats. And I think stabilizing a large number of complex structure moduli will be impossible. And again, all these calculations, they could have given pro-landscape results or anti-landscape results. Some of them gave us pro-landscape, some of them gave us anti-landscape, but I think it's time to think, to basically stop. I mean, people had a nice intuition. Some of the intuition is good, some of the intuition is not. People should just step back and ask, how can I change? How can I come up with a new ingredient? And the conclusion is, I mean, if I want to leave you something, I think we have to go back to the drawing board. I think one has to calculate, again, as Sandeep was saying, singularities, complex structure modular stabilization with confinement.
By the way, don't quote me out of context. I don't think there's anything fundamentally wrong in the KKLT idea so far. I don't think any of your criticisms really hold water at the level of in-depth analysis and proof, but sure, one can look at other scenarios. Is there a proof that de Sitter vacua exists? No, there is not. But none of what you mentioned, as every point you made, we went over. There's no proof there. There's some conjecture. 1/3 is a number. In these examples is violated. Not a proof, okay? This is the content. So let me say, please don't quote me. I am not suggesting there's something fundamentally wrong in KKLT. I want this recording to clearly mention this fact. Okay, thanks. Just go ahead. I think your conclusions on this slide are unwarranted in view of your talk, Iosif, frankly. Not held up by the content of your talk, but please go ahead and
again. I think those are all the points people. I mean, I think those points are actually made to us by, again, they are written, they are given in talks. I mean, this is the standard law of the field. All antibranes are okay.
We went over each of them today. Sometimes it's metastable. For large M, it's not. So there's that. You know, there's no. I mean, please. All right, go ahead.
No. The point is,
it's okay. Conclude. I'm not going to say anything more.
No. The only thing I'm saying is that, you know, there's a standard law. And the calculation showed that the standard law.
You quote things as if it's standard law. I mean, I won't agree with that characterization. You know,
people said
we knew when we wrote the paper that supergravity would be valid if you needed a big flux, for example. Okay, we knew that if you had more than one anti-D3 brane, there could be forces. So we said, to be conservative, start with one anti-D3 brane, etc., etc. Okay, so I mean, to say there was some other law and it got upturned and so on, it's a mischaracterization.
Okay. Let's put it this way: given the opposition we had when we said that multiple anti-D branes are not okay, given the opposition we had, I don't think it's so clear as you said.
Even for the multi-D3 branes, it's only an issue of how they'll be spread out on the compact directions, okay? And then, yes, there is a tunneling possibility when M is small of brane flux annihilation, but that had been calculated already, which is why one knew you need big flux, and anyway, you need big flux to control supergravity. So I'm just saying, you know, let's be a little careful about how we characterize things, but go ahead, please.
No, that's the only conclusion I had. I mean, essentially, I think that at this point, the existing constructions, I think one needs to find new ingredients. And again, this anti-D brane uplift, for example, using bubbles, I think it's a new ingredient. I think we don't have to just say, 10 to the 500 universes and everything is hunky-dory. One has to be careful. And I think there'll be some, I mean, I'm sure there'll be some de Sitter thing. I mean, otherwise, I mean, if it quintessence will be the answer, I'll shoot myself. But I think that one has to be careful about how the calculation is done. And I don't think it will work in all examples. And I think this will put some nice constraints. I think, of the 10 to the 500 vacua, I think there'll be a few of them which have de Sitter. But one has to be careful. I don't think the arguments work with the bulldozer. Say yes, everything works. All the flux compactifications work. All the fluxes work. Everything is nice. Just find the long throat. Put an enderbrain. You just give you every Calabi-Yau you can think about, and every flux choice is going to give you a nice contribution. That's what people said who are pushing the landscape idea. What I'm saying is that all these arguments have holes. All the arguments which have been used for the landscape idea have holes. Now, I'm sure there'll be, I hope there'll be some other compactifications. I think KKLT will work ultimately, but it will involve non-trivial ingredients. It will involve non-trivial physics, looking exactly how the details work. It will not be that every single Calabi-Yau on the 10 to the 272,000 Calabi-Yaus is going to give you a nice vacuum, and it will give you a de Sitter compactification and would stabilize moduli. I don't think that will happen, and I think you agree with me on that. Of all the possible 10 to the 500.
I'm not saying in every Calabi-Yau you could do this and so on. That's not the claim. The claim is that in some, and I agree, nobody has an example where everything is under control. I agree.
And I think the landscape idea.
You have proved that every parameter we think.
No. I'm not saying I'm proving that.
By the way, let me just say why it's so hard to do. Okay, let me now say what is the central drawback of KKLT. It's none of what you've said, Iosif, with all due respect. It's the following. There is no parameter. There is not a parametric control on this class of compactifications. Okay, without parametric control, it becomes very hard to say if I was claiming some parameter is small enough to control an effect to be really sure. The only way to be sure is that you have to compute the corrections due to that parameter and show that the consequences don't change your original conclusions. Nobody can do this. For example, loop effects in the presence of Ramon backgrounds are extraordinarily hard to do, right? And so on and so forth. So we are very far away from actually being able to test conclusively whether compactifications with control can arise, but it's not the issues you raise.
But I think if you have a classical solution, so at least, if you have, I mean, if the Denef-Douglas calculation gave us 10 to the 500 classical vacua, which are all have classical stabilized moduli, I don't care about loops. I mean, loops are going to give me some result. If I had gotten 10 to the 500 moduli with stabilized,
you have to care about loops, because if we are saying, you see, there is not a parametric control on how small G string can be made. So if we are saying G string is small enough, okay, that has to be taken with a grain of salt. That means compute the loop effects with this value of G string in the Calabi-Yau and show that the potential is not getting a big contribution at the next order. This is not something anybody can do today.
Indeed,
so
but
that is why it's too early to conclude that we have definitive proof. But it's not these kinds of issues, with all due respect.
I think these issues are classical. I mean, what you're saying is a second order issue. I mean, these issues are actually more fundamental. If you have a classical vacuum,
anyway, okay, fine. All
if you have a classical vacuum with stabilized moduli, I don't care about loop effects. I mean, if all my moduli are stabilized, if all my 2,1 moduli are stabilized.
EM has many beautiful examples. He even gives the W naught to be very small. So, people are already making a great deal of progress. He got W naught to be 10 to the -8. He's probably going to get it to be even smaller.
Yes, but I think the problem is, the vacua which give it 10 to the -8 W naught. If you look at the mirror dual, for example, I think they have the Tadpole problem. But okay, that's something.
Who wants to look at the mirror dual? I look at the version he looks at. Okay.
But if the mirror dual has closed time curves, then that's. I mean, people don't build these Calabi-Yaus. I mean, the whole thing about the Tadpole conjecture is that there's a constraint. You cannot just put any fluxes you want.
No, but he needs the anyway. Okay, no, I don't agree. I don't agree. There's anything wrong in his constructions. Okay. All right. Okay.
Okay. I think that is the conclusion. The conclusion. I think there's more work to be done, and I think I think just dumping ingredients with the bucket. One needs to be careful, and one needs to. I mean, it will not work on the biggest, fattest, more generic thing. I think one needs to work exactly to find out when it happens and how it happens. But I think that's a conclusion to which we can all agree.
Okay. Thanks a lot, Iosif. I have to run now, but thanks a lot for a nice talk. Thank you.
Thanks so much, Iosif.
Thanks a lot, Iosif, for a very nice
I guess
talk.
we stayed for 1 hour and 40 minutes. Wow. Okay, that's like a Saclay seminar. Saclay seminars usually take 1 hour and a half, but.
Thank you very much for agreeing to this, and thanks for answering all the questions so patiently.
Sure. Keeping the fight. How are you guys doing? How is everything going on?
All great. Back to normal. And
okay.
How are things with you?
Fine. I was telling Sandeep, I'm trying to finish up. I mean, I have 2 postdocs applying, so two close collaborators applying. So I'm trying to finish up the papers with them so that before the market time. But I'm very happy with this brain anti-brain stuff. I mean, it's good for fastballs and it's good for flux compactifications. And I think, I mean, it's really like something which I didn't have any hope it could be built. I've been trying for 15 years and without any results. And finally, Ibu and Ibu and Pierre, they have these solutions. Finally I see some light. At least some solutions where one can make some progress. Maybe they're unstable, maybe something else happens, but at least I have something. So I'm quite happy. There should be some way out, both from the flux compactification story and also for the fastball story. But that's.
I have a question regarding the value of the potential when you compute the expectation values of the various scalar fields and you insert them in the potential, that should give rise to the cosmological constant, right?
Oh, that's a negative cosmological constant.
Yeah. So it will give rise to a negative cosmological constant, so my question is, does that term receive contributions, say, from the expectation values of the fermions as well?
I think it's a classical
calculation. Computing the
boson. I think it's a classical calculation. If you look at this let me look here. No, sorry, where is it? Where do I have it? here? No, bare bones. I'm trying to find the place. So there's a classical calculation, which just tells you the classical potential. And then you can compute corrections. As Sandeep was saying, you can compute corrections on top, and maybe.
That I agree. Yeah. All I'm asking is,
But,
you finally compute the total potential. Do you ignore the fermionic terms, or do you include?
No. So the classical calculation doesn't have any fermionic terms. So you do a classical calculation first. You have a potential for all the scalars, and then you can ask what's happening at one loop. Do you have the fermions coming in? Can they mess up this potential? Now, personally, if the classical potential is big and fat, quantum corrections are small. It's in some control limit. Everything should be hunky dory, but one doesn't know. So generically, if the fluxes are going to be very small, I mean, if this Calabi-Yau will have very, very small sizes, it will be if it will be like a very, very small Calabi-Yau, then I'm just trying to find where is this thing here, yeah. So if this Calabi-Yau is going to be very, very small, then okay, there'll be some problem, and you need to break. You need to break. You need to look at setups when the corrections are higher than the tree level. But for example, in this example which we worked out, there's a nice big fat classical potential. So that's even if you have corrections, this will not be destroyed. That's a generic standard law.
So you include the fermionic contributions. That's what you're saying.
No. At tree level, you don't need to do, because it's a classical calculation. So you do the classical calculation.
Finally, I agree at tree level you really don't need to, but finally when you compute the loop corrections and the flux potential corrections, etc.
But those are very hard to compute. Those are very hard to compute.
The fermionic contributions will make a contribution, right?
Absolutely.
The one
and the
loop
bosonic also, and all the guys. Yes, I mean it will be a messy calculation, and that's what I think what Sandeep believes, that there'll be a problem with KKLT. Maybe he says that these things are not known, and these things are not under control.
Okay.
That's
okay. Thanks again, Iosif. Thank you for your patience.
Thanks a lot, and see you guys around.
See you.
Okay, bye.